filling in.
One day we have 2 minutes of push-ups and 2 minutes of and then 2 minutes. I don't know.
So today we'll be talking about potential energy conservation events. I know the last few lectures we've been talking about forces and the kinetic energy. And so, does anyone remember kind of the definition of power and kinetic energy? So kinetic energy has to do with the motion of particles, right? So some particle has some velocity and it has mass. So potential energy is certainly different than that.
Look at him roll along. You know how annoying that is?
Maybe so. That means that does anyone kind of have a good operational definition of potential energy before I write up the textbook? The energy of the body by virtue of its position. So that's it's along the right line. Now, when you say by virtue of its position, with reference to what? You're absolutely going the right path, but there's a little more to it. And when I write it, it's going to sound kind of jargon.
Does he have a microphone?
Getting at what you're saying, but so maybe we'll keep that for a second.
Can you speak loud?
Okay. Ability being kind of like potential, like a ball sitting at the top of it, or has that ability if it were to start rolling, it could create a again, it's along the right line. So I'll write up the textbook definition. It's probably not going to sound great, but I'll get to the key points and give you an example that will sound like So in your textbook, I forget what page, but it says that potential energy, so I'm going to just use U for potential energy, so you're paying for kinetic energy. Potential energy is the energy associated with the configuration
Where you
of a system of objects.
get lost? What are you doing now? You're behind. Just plug in your head.
And the forces that act between them.
Just say simple physics.
So it's a long definition. Okay, so a couple of things. This isn't necessarily something you want to know this, it's not word for word, but a couple of key points. This term configuration we'll get at in a second. This is very important. System, okay, and then forces, internal, that are acting between these particles in the system, okay? So let's let that marinate for a second. We'll talk about an example that hopefully puts this in much better context. So the simplest example that I know of is just something we deal with all the time, is tossing an object in the air. So if I draw, let's say gravity is acting this way, okay, and I have some ball that I toss up, has a mass in, and when it's going up, let's say I'm going to call this process number 1. Okay, so I toss it up, and then it falls, and it goes through some height, let's say h. Okay. So I toss the ball up, it reaches a stopping point, turns around and falls back down. Now, during this rising process, okay, so let's say 1 is the rise, what is the gravitational force doing to that object? Decelerating. Okay. So in terms of, and that's right, in terms of work, so we want to phrase things in terms of work. So we're going to eventually have definition connected to potential energy for work. So can you rephrase that in terms of the work? That's right. So the gravitational field that we're approximating as constant towards the Earth system. So I should be careful to say the Earth is creating. So there's a second body. Remember how I said that system is very important to understanding potential energy. So what I haven't really drawn is the thing that's generating, or part of the generation of this gravitational field, is the Earth system. So we have the Earth and then the ball that I'm tossing up. And like you said, the gravitational force, so I'll just say the G, is doing negative me, why is that work negative? There should be a couple reasons that stand out immediately. Yes? That's right, okay. So it's opposing, you're saying that the force due to gravity is opposing the applied. So what's the applied force such that I tossed it?
Yeah.
I gave it an initial kinetic energy, but once I let go of it, I'm no longer applying a force.
Well, then it's opposing the force of motion.
That's right. So and you're absolutely correct, the displacement vector, right?
Yeah.
So in terms of kind of what we're doing in this class, a quick way to say the ball is my work positive or negative. And if you look at this vector, it's pointing down, but in process number one, the ball's going up. So we have opposite, so F, G, and D are opposite, right? So that tells you right away, we must be doing some, this force, gravity, is doing some kind of negative work on that. Also, you could look at it as, well, the ball eventually stops, it doesn't just keep going. So something is removing kinetic energy from it, right? We gave it kinetic energy, there had to be something that removed that kinetic energy. So you could either argue that, well, the force and the displacement vector are opposite, or that we're removing kinetic energy, and that's why it eventually comes to a stop at some distance. We don't really care about h, right? So those are the two ways that you want to reason that this is doing negative work. Now, let's see. So what we'll get to later today is that the other part of that is it's removing kinetic energy, but it's actually taking that kinetic energy and transferring it to something else, which we'll end up calling potential energy, right? So the potential is being stored. Now, when it reaches this apex, it has a lot of potential energy because it wants to fall back down to the Earth, right? So in the second part, which is called this process here, when it's falling, all right, now is the gravitational force doing positive or negative work in process number two? So we said negative in process number one, so oh, I'm sorry. This is, so I'm just calling the Fg as the force of gravity, which here is just mg. And then d is my displacement vector. And this has, I'm just saying, those two things are, I should maybe say commas, you know, being dividing. So these two vectors are opposite. Because here, if I wanted to draw a displacement vector, it would be that. So can we use d for the displacement vector? Okay, well, for today, we'll just say these are displacement vectors going up. But the main point being is that they're pointing opposite of each other. Okay, so in the second process of the fall, we know that the force due to gravity on that mass is doing positive work, okay? And it's for the exact same reasons as in during the rise, except opposite circumstances. So here you can see, if I do a little displacement vector, it's pointing down. Gravitational force is pointing down, so they're aligned, and that means we're doing positive work. You could also look at it as it would stop when it reached the apex. Right? For that instant, you have no velocity, no kinetic energy. We'll get to it later, but it's all stored potential energy. And now we're increasing that kinetic energy to have it go backwards. Okay? So I'm kind of belaboring these points, but it's really, a lot of people have trouble with potential energy because definitions like this don't really seem to mean a lot to people. But it's good to keep an example like this, and then all these kind of subtle points in between to understand the differences. And we'll get in a second how potential energy ties into this. Okay. So like I said, the other part of this, the other half of it is during the rise, gravity's doing negative work, but it's transferring that kinetic energy into potential energy. That's stored in a system. It's not that this object by itself has some potential energy, right? So if I had to say, well, what are key differences between kinetic energy and potential energy? So I kind of just said one of them. I mean, if you told me the velocity of a particle and it had some mass, I could immediately tell you it has the kinetic energy this, and we write it as 1/2 mv squared, right? If I said, well, what's that particle's potential energy? Does that question make any sense at all? If I just said, here's a particle out in some arbitrary space, what's its potential? So you should be saying no, it doesn't make any sense, right? Because we need this configuration where it just means you have some system of particles. So again, here, although it's not drawn, the system is the Earth and this mass, right? So without the Earth being here, you could look at that mass just out in some free space. Let's pretend there's no forces at all acting on it. It just has some initial velocity. Then it has a kinetic energy. But if I ask you again, what's the potential energy? I need to tell you a system, right? And so here the system is the Earth body system, okay? That's one of the key differences. Now, let's see. Did everyone get this copy down? Actually, this definition is less important. So I'll erase this. So what we'll have, hopefully you recall that the kinetic energy work theorem is that work is a change in kinetic energy, right? So today what we'll be talking about is similar to this, potential energy, or the change in potential energy, because really it's the change that has meaning. The change in potential energy, which again I'm using U, hope you're familiar with that, is equal to the negative, okay? All right. So if you look back at our example, if the gravitational force field is doing negative work on that particle, but it's the negative of the negative work that changes the potential energy. And kind of like what we were getting at is, as it's doing negative work in process number 1, it's increasing the potential energy. So negative and negative is increasing the potential energy here. Just like in process 2, if the gravitational force is doing positive work, then it has to be decreasing, right? So the change in potential energy was at its maximum at the apex, and then it's at a minimum when it falls back to Earth, right? Okay, so these are certainly definitions that you want to have, or equations that you want to have written down. Okay, so we've talked about this simple body system. Let's get into a little bit different. I mean, it's a little more complicated system, and I'll have you guys kind of walk through it, of course. So can I erase this or Gary?
Does that mean that, because of those two equations, does that mean that negative relative to equals
That's right, and we'll get to that. So we're going to talk later about conservation, and you have to be careful. And some of the things we're going to talk about in a moment are conservative versus non-conservative forces. So even the idea of potential energy, right now I haven't talked about conservative or non-conservative forces, so we have to be careful with that, saying they are equal, and it certainly looks like it right there. But this is given a big assumption that we're using conservative forces. Okay, and I'll touch back on that in a second after we go through another example.
Okay.
Do you guys have this down enough? Can I erase this and we do a second example? Okay. All right, so the second simplest example you can probably think of is a spring mass system. And so here I'll draw some x-axis going this way, so positive x-axis to the right, my right. And then we have our 0 here. And let's say we have some mass M, spring, and wall. Okay, and you notice I've displaced it from its equilibrium. And in this setup, let's say I give it an initial velocity to the right. Okay. So in this system, just like how we went through and kind of belabored with the Earth ball system, we have the spring mass system here. So what I want you guys to help me walk through is one, we're going to label all the forces that are relevant to this work, energy, potential energy kind of system. So all the forces, the different types of work that are being done, meaning positive or negative work, the change in kinetic energy, and then finally the change in potential energy. So these are things that are very common in homework problems or on tests. One of the first things you want to assess are all the forces, which you should be used to by now from the last 2 chapters. But we're adding in these concepts of work and energy transfer. And so these are all things that you want to be able to immediately assess. So in this setup, as I've drawn it here, we have a compressed spring. Can anyone tell me, so one, I'm going to do a second example. We're going the other way in a second, so I'll say this is 1A. Can anyone tell me the relevant forces in this setup? I say relevant. Yes. Okay, and that's exactly right. So there's more than just the force of the spring. We certainly still have gravity acting, right, downward, but the normal force is balancing that. And so, I got to be careful. This is frictionless, by the way. Okay, we'll get to friction and how it plays a part later. But here, we can completely ignore the normal force and the gravitational force. So I'm not even going to draw it. I don't want to make it any more complicated than it has to be. The only force that really matters is what we call restoring force, and that's by the spring. Okay? So I'm going to just say F. Maybe I should, since that's a static friction. F spring. Okay? So that's opposing that motion. And so that's the correct force. So we're done. F spring points to the left. Okay, so what about 2A? Now I'm focused on the mass. That's the thing that I'm interested in. We know that this string is being compressed. And so it's applying a restoring force to the left. Just like the ball being tossed up, what kind of work now is not Earth, but the spring doing on this mass? Okay, so think about it in analogy to the ball being tossed up. So if I gave this mass, I push it, I give it some initial velocity, and I let go of it, so I'm no longer applying the force in the x direction. I just send it in, the spring is catching it. What's happening to the kinetic energy of that mass? It's going down, yeah, it's decreasing. Something is removing kinetic energy from it, right? That something is being the restoring force. So again, we want to isolate the things that matter. It's the force that's affecting this mass or taking that kinetic energy from it. Okay, that's important here. The gravitational force is there, but if it's frictionless, we say we don't really care about it at all when we do it. So certainly the work here is done by the spring, and now is that work positive or negative? It's opposed, right. If I drew a displacement vector underneath, I mean, I don't want to get this too crowded, but the displacement vector initially is going to the right. Clearly the spring force is opposing it. It's taking kinetic energy. Has to be that it's doing negative work. So work here is negative. Now we kind of already answered this. So 3A should be that the change in kinetic energy, is it decreasing or increasing? Decreasing, exactly. So we're decreasing, which was how we kind of argued that the work was negative. And then, now here's the last part that, until today, presumably, this is something new, is the change in potential energy. So, if this kinetic energy is decreasing, we know the work is negative, then we should immediately be able to use one of these two equations to tell us what's happening to that change in potential energy. So is that increasing or decreasing? I'm sorry, yeah, right. Exactly. So, I mean, they're certainly opposite. It has to be opposite of the work being done by that spring. So we'll say that the potential energy is increasing. Kinetic energy is being taken from the mass, and we're storing it in what's called elastic potential energy. So that's a term. Elastic potential energy just means we have two dealing with springs, right? As opposed to what we were dealing with before we eliminated maybe gravitational. And later we're going to derive kind of a formula for elastic potential energy. But right now, you should just be able to feel that. If I send a mass into a spring, the mass is slowing down, something's happening. It's not magic. I mean, that energy's going somewhere. It's being stored in the coils of the spring as elastic potential energy. Okay. Now, this is the first example. Now let's say it reaches some stopping point and turns around. So my displacement vector is this way. Now, the spring is pushing it along, and it's going to the left towards its equilibrium point. Now, I purposely drawn it like this, so be careful, because this is one of the things that it's important to know exactly where your equilibrium is in the situation. It's not as obvious now, maybe, but I'm making clear that we haven't reached equilibrium, we're just heading back in that direction. So, let me erase it over here so we can compare them one by one. So we have, in situation 2A, is the force, or what direction is the force of the spring now? I'm sorry, what's that? Yes. So it's still to the left as it's drawn here. Now, if we had crossed this equilibrium point, and now we've extended the spring past equilibrium on this side, it would be, I mean, by definition of being a form of restoring force means it's restoring it back to an equilibrium. It wants to be at the equilibrium, and we haven't reached it yet, so it's still pushing it along in that direction to try to reach the equilibrium, right? So So this is the same, exactly the same. That spring, in this case, is still to the left. Now, for 2B, now things are probably not the same. So is the work negative or positive in this case? And why is it positive? So you're saying the force is the same direction as the displacement vector? Yes, that's absolutely correct. Now, is there a second argument that you can make for that? That's right. So we said it stopped at some point here, meaning at some point it had zero kinetic energy. It came for that one instant, at zero kinetic energy came to a stop. Well, by the point that it's here, it's now has some kinetic energy. So we've increased its kinetic energy. And that's because these two forces, the force and the displacement vector are in the same direction. So it's increasing that kinetic energy. So the work is positive. Okay. Now, we've already answered this part. We know that that means we're increasing the kinetic energy of that mass. And okay, so then in the last part, if we're increasing that kinetic energy, what does that mean about our potential energy? I'm sorry. Exactly, it has to be decreasing. And we know that because we're just stating that, just like we stated that the work is a change in kinetic energy, we're stating that the change in potential energy is equal to negative of the work. So these two better be different, and in this case, we're decreasing. The greatest elastic potential energy that we ever had in the system was in that one instant where the mass completely stopped. It gave all its kinetic energy into the spring, it was stored in the spring, and then any time after that, it's always less than that potential energy. Right? It had its greatest potential at that moment. And again, it's important to see, if the spring weren't here at all, and I just slide a mass along the ground and take friction on the wall there, well, it's going to slide into the wall, that's all that's going to happen, right? There's no, to make sense of the potential energy, you have to have a system in mind. Okay, so here the system is very simple, it's just a mass in the spring. Before the system was the Earth and the ball. Now, I'll give you a second to write those down. And after that, we're going to talk about what I was mentioning is the conservative versus non-conservative. Because all of this was kind of based on the assumption that we're dealing with conservative forces. And most of the time throughout this course, we'll be dealing with conservative forces. It's by far a lot easier and gives you a lot of nice equations that you can come from that. So, has everybody written down this right-hand side? Let's see that. Is anyone familiar with the difference or the definition of conservative versus a non-conservative force? You guys, is that something you've encountered before in high school courses or any courses before? Maybe some vague kind of definition that you had at one point and it's gone now. So we'll touch back on that. So I'll go into that with using the examples that we already had, which was that the ball being tossed up in the Earth mass system. Okay, so if we have some mass, and we had process 1, and that was when it was being tossed up, and then when it falls back down, this is process 2. Now, I've erased it from earlier, but we said that there was some type of work being done in process 1, right? Whatever it is, we'll call that work W1, right? And then when we complete the process of tossing the ball up, we'll call that second half process number 2, and that has associated with it work 2. And again, when I say this, I mean work done on that mass by the gravitation wave. Okay. So, as sort of a definition for conservative versus non-conservative, in order to have a conservative force, if you have any type of process like this, where we go up and then we completely reverse that process and undo it by a second process. If you have the case that W1 is equal to negative W2, so this is important, we definitely have this down. if you have this, and it doesn't matter what you do, but when you reverse that process, that they're exactly equal but opposite of each other. The work, not forces here. This is Newton's third law. So if the work is equal but opposite, then you have a conservative force. Yes, you have a conservative force. In this case, the gravitational force. Okay. So in our two examples, and we'll get to more rigorous kind of definition later, but in our two examples of tossing the ball or the mass spring system, can you guess whether or not the two forces that were relevant there were conservative or non-conservative? Assuming there wasn't friction again in the second example. Yes. Yes, and I haven't really given you the equations to prove that yet, but you can kind of feel that and we'll look at this example, check it in a second, but you're absolutely right. So the spring Hooke's law equation, assuming there's no there's no friction there, that's a simple harmonic oscillator. And that system, if I were to set it into motion without any friction, ideally it could just continue forever. And so when it continues forever, what it's doing is it's always reaching that initial point and it's starting over. And so whatever I did in one direction, it's undoing in that second direction. It could continue indefinitely. Okay? So that's perfectly correct. And when I have this written down, that being said, can you think of forces that are non-conservative? So I've kind of already said one, right? That's right. So the kinetic friction force. Static friction doesn't really play a part because we're talking about work, we're talking about moving objects that are moving under the influence of some force. But I'll give you two examples. One of them would be, if I had a mass sliding across this floor, and this is a real floor that has friction, then the kinetic frictional force acting on it would certainly be non-conservative. Okay? And the second one is the drag force. So hopefully you covered this, I think, in class. I think you have a homework problem this week that involves the drag force. But the kinetic frictional force is a little easier to think about. So keeping in mind like the spring mass system that's ideal, that I could set into motion and continue in motion, or a pendulum, that I could set into motion and it would swing forever if it were ideal, there were no drag force from the air, or there were no friction from the spring with the ground. In that case, again, we have that the work part, and those two processes are completely the same but opposite. With kinetic frictional force, if I were to take a box and slide it across this floor, it comes to a stop eventually, so we know there's friction there. Now what's happening is that between the box and the floor, we're heating up, right? There's that cold welding, it's ripping and it's heating between the bottom of the box and the floor is both heating up. Now, let's say I took that box and I attached it to a spring mass system, or I take a mass and I give it friction. Now, if it goes to the right, like it did in our example, it would have some certain work, but it's also heating up the floor. As it turns around and it goes to the left, could it ever possibly undo the work that it had? Can it kind of recollect those random thermal motions that are occurring, take all that, store it back up, and change it into exactly the same order? No, I mean, it's certainly impossible. That is what we call, if you want a definition, it's an irreversible process. So when I make those random thermal motions between the atoms and molecules colliding, I can't then just undo that, piece them back together, put it in to make them exactly the same. Certainly the mass would go and it would damp out and come to a stop, okay? So kinetic frictional force is a non-conservative force, drag force is the same. So with that being said, we'll talk about some tests for how to identify conservative forces. So that if you're dealing with a force or a question on a homework or test and ask, is this a conservative force or not? You'll have a quick test to figure out whether it is. So I'll write the definition from your textbook for conservative forces. Okay, so for conservative forces, we say the net work done by a conservative force the net work done by conservative force on a particle moving around any closed path is 0. So conservative force, the net work, and then closed path. Are you guys familiar with what closed path versus open path or any other type of path means? Okay, so in our first example, or in both examples, when we toss a ball, right, it reaches some apex, assuming it falls right back down to that same point. That system, it's gone through some closed loop. It's maybe easier if you think about the spring like a perfect spring mass system. If I set it into motion, I give it kinetic energy in one direction, and if it were perfect, or a pendulum, it would come back, it would go back and forth forever, right? Indefinitely if there were no friction. So every time it starts over, it goes to that same initial condition. Then you've started over, you've gone through a closed path. If I just sent the spring, the mass one way, and I just stopped it, let's say at the end, and I say, well, it didn't undo its work, it's not a conservative force, that's not fair, right? I didn't let it come back to its complete its closed path. So the network, because there can be many forces acting on it, but the network done by the conservative force on the particle around a closed path has to be 0. And we'll get to, in a second, of how we can use that for our benefit in simplifying a lot of problems. So, do that. We have this written, actually, I'll do it again. With the example, to prove to you, I guess in the ball being tossed out. So if we toss the ball from some height, we all kind of qualitatively knew what it would do earlier, but here would show why it has to be the case. So assume that I toss it up with some initial kinetic energy, Ki. I give it some initial velocity, V. So it's 1/2 m VI squared, right? Now, as soon as I toss it, I'm no longer applying the force. I toss it up. It has this initial kinetic energy. What we'll do is we'll define in this system the potential energy here, and I'll get into this a little bit later. But we'll define it when it's touching the Earth. Let's say that that's the 0 potential energy. Okay? So we're measuring from the surface of the Earth, falling to 0. So as soon as I launch it, its kinetic energy is this, but it has no potential. Right? Now, what kind of force do we have acting here again? So it's just the gravitational force. Gravity we're approximating is a constant force. So what kind of equations are we allowed to use when we have constant forces or constant accelerations? These are equations you absolutely need to know for the test that you're going to have. That's right, so your kinematic equations. Now, the ones that would be useful for this case is we'll use V final squared minus V initial squared equals 2a, and we've gone some distance h, right? So this should be review. So that's our change. Now, what was our, let's just say I'm looking and I'm saying I'm going from here to here, at the apex, this is where I'm measuring, this is the equation. So what's our final velocity there? 0, exactly. So we get rid of this guy, we have negative VI squared equals 2a. So we stop, that's process number 1. Okay, so you can't just let it go and then say I'm measuring from here when it's hit again. We need to look at the first process, say negative VI squared equals 2AH. Okay? Now, if the ball is falling down, in the second process, you write the same equation, but it's kind of the opposite situation. So here, there's a subtlety, and you should be careful of this if you encounter anything like this on a test. What can I get rid of here? I'm saying I'm starting from the apex, it's falling against the ground. Yes, VI. The initial velocity in this case is 0, right? Now, if this is the case, then what I might, in error, do is say, okay, my final velocity is equal to, well, 2AH. This is common between the two, so let's set it equal to negative VI squared. Well, that's kind of a problem, right? Can anyone tell me what it did wrong there? It's the subtlety and the definition of, again, being careful when you have systems of particles where you measure from and do it. So if I were to take the square root here and say my final velocity is some complex number, and that's not physical, so that doesn't make any sense, right? So I did a subtle error here in how I'm defining these two processes, which is again important in understanding how you get the work between these processes. Does anyone see? Yes. Exactly. So when I say I toss it up, and the Earth was my 0 point, right? X equals or Y equals 0 here. This distance of h is positive. Now, in the second process, I'm at h and I'm going to 0. So, you know, I should have written this out in the first time and said this is 2a y, you know, minus y naught, or y1 minus y naught, something like that, so that you know you have to go from where you're at in the second process. So like you say, here, this is actually negative 2ah. Putting that in, I get positive. This means that Bf is either plus or minus Vi, and by the physics of the situation, it must be opposite. Okay, right? It's falling down, it has that displacement. So, what have I shown? My final velocity in the second process was the same as my initial velocity. So, for the first process, it's all kinetic energy. As soon as I launch it, there's no potential. And it has some initial velocity, so the kinetic energy here was this. Now, if I want to say, what's my kinetic energy in the process 2, I've shown that it's exactly this, but opposite, right? And so, it's exactly the same as you square it. So then if I were to say, what's the change in kinetic energy, that would be 0 in this process, right? And so if I'm looking at the work is that change in kinetic energy, so the work between the process is 0. And hopefully you have it written down, but it's here. The net work by conservative force without any closed path is 0. So this is kind of just a little crude example to show you can prove for the Dalton toss-up very quickly that the network is indeed 0, and so we can say the gravitational force is conservative. We don't have time to do the spring mass system, but you can do the same thing for this. All right. So hopefully you have a better understanding of conservative forces, and I will get into a second of why this is helpful. Okay. One of the consequences of having that around any closed path is 0 is this, and I'll write it out. The work done by a conservative force is moving between any 2 points as a consequence of what we just worked through. So if I take this path, maybe you've seen this before, I'll call this A, I'll call this B, here's path 2. They're definitely different. Okay? They can combine together to make a closed loop, but if you focus just on this particle as some force, I'm not saying it's gravity, but I'm saying it's conservative, right? Whatever it is, we don't care, you just need to know it's conservative force. And the particle moves by path 1 to B, okay? Or it moves by path 2 to B. So the nice thing about having conservative forces is you can say, I actually don't care if it takes path 1 or 2 or any of the infinite paths in between. I only care about these 2 points, the starting point and the ending point. That's a consequence of the closed path test, and that the network is 0, okay? So we'll do a real quick proof for this. You can say that given that it's conservative force, A to B by path 1 plus B to A, so we're going backwards, to B to A by path 2 is 0. Now that's the statement of a conservative force, right? That's what we're going to talk about. This is a test to say that you have conservative force. So I told you it's conservative, so this is certainly true. Now, if that's true, then WAB1 is negative WBA2. Okay. Now, if we were to just focus on the path A to B through 2, what you can say about that is that WAB2, if it's a conservative force, has to be equal to what in relation to WBA? Now notice I flipped the indices. I'm going one way, it's doing work on the particle through this path. I've completely reversed that path. So what am I missing here? What's that? Yeah, exactly. So this is just a statement of conservative force. The work done, if I reverse that process, has to be perfectly negative of it. So if WBA2 is negative at this, I can put a negative in, BA1 is negative of the negative of AB2, which is positive AB2, okay? And so this is a really important concept that comes as a consequence of using conservative forces. This is not the case if your forces are non-conservative. You can't make this statement. And again, you'll see in problems that you'll do later, especially after doing all these weeks of Newtonian dynamics, that when you're dealing with energy, and this is something they call path independence. I don't care if I go here, or here, or here, or up here, as long as I started here and I went there and I have conservative force field, then this is the case that my starting work, the final work, or sorry, the two paths, the work done is the same, okay? And so in problems where you had to worry about forces and all these things happening, but maybe the 2 points were the same, you could quickly get to an answer using this kind of this path independence, okay? Let me check the time. So I have an example for that, but I'm afraid we're running a little short or a little behind, so I'll skip that one. You can look into it yourself and convince yourselves that if you had some block mass system, your normal force of gravity, and this block, let's just say I shot it onto a ramp. I'm not applying the force, I just sent it onto a ramp, some kinetic energy. The work being done by the gravitational field, to get that block from here to here, you can calculate it, right? Now let's just say it came along here, I launched it with some camera or some device. Again, I'm not applying the force, I'm just giving it a kinetic energy. But let's say the mass ends in the same spot up here. In one case, one path, it went up this slope. The slope could be 5, this could be 4, this could be 3 meters or something. So you should work it out if you get a chance. Convince yourself that this works. If you do this, you'll find that the work done to go up this slope versus the work to go straight up against gravity, okay, because the gravitational force is reduced here, they're exactly the same. If you use what I did, which was 10 kilogram box and a 3-4-5 triangle, you'll get that it comes out to over 294 joules. So, but for the sake of time, we'll move on to a lot of other stuff. So go ahead and erase this. Okay. So you may be familiar with this, but we're going to do something that's very useful. It's the calculation of change in potential energy from some known work. So finding U from W. All right. Now, for a general force that varies with position, I'm sure you've covered this. This is in general from x initial to x final dx, right? So if you substitute in, now if you use that the change in potential energy is negative of the work, all I have to do is take a negative of that, and I can say that the change in potential is negative from some initial to some final dx, okay? And this is going to allow us to take common forces that we know, like the force of gravity or the force from a spring, and calculate what our change in potential as a function of position should be. So let me erase this. So starting with the gravitation, assume here, I'm going to speed up a little bit, that we have some initial point, we have some final point. We have gravity acting down, right, on the mass. So we're in a gravitational force field, and I'm just saying my particle had some initial velocity. I want to know its change in potential energy when it goes from this initial position to this final. Okay. That's all I need to know about a system. Here's the x-axis, but it's kind of inconsequential here. So given that equation, changing everything from x's to y, I can say that my change in potential energy is equal to negative y initial, y final. Now what is my force as a function of y? That's right, so it's just constant. In the y direction, that's why I'm saying just going along y to make life easier. I could go along in some skewed path, but then I'd have to get sine and cosine. So now, this is also going to be mg, but in this system where y is positive, I'll call that negative mg, right? So again, a small, you have to be careful with that. So mg, that's a constant, comes out of the integral. This becomes positive, and then I'll have mg y from y initial to y final. And this is just mg, and I can call that defined as change in y. So you may be familiar with this formula for dealing with an Earth mass system. You toss the ball, you want to know the potential energy. It's mg times the height, change in height. So I'm here to keep. Now, I said that it's really only the changes in potential energy that matter, not some absolute point, because I can change my reference. And when in our original definition, when we said we had a configuration of particles, you have to, it's convenient sometimes to have a reference configuration. So with these types of problems, we'll call the ground or the earth or wherever is convenient to be the zero. So what I can do is say, well, my u at some point y relative to the initial point which I'll call the zero at x is equal to mg, and this is y minus some initial point. I'm just expanding this out, right? But here, the convenient choice, which we use all the time, is we'll say, okay, it's 0 when y is 0. And then this is maybe a more familiar form. It makes it look like you're, I mean, it's kind of bad, it makes it look like you're just measuring potential energy at one spot. It's still a difference. It's just assume that you're taking it with reference to the ground. Okay? So if any of these work, this is probably the most basic, the most common form that you see. It kind of tricks you, though, into thinking that you're just measuring it at one point, which I said wasn't very meaningful. Now, quickly, can anybody tell me, did I cheat a little bit when I just went from here to here along the vertical axis? I mean, that's, I'm telling you, this works for anything, any talking about anything where we're putting something above the Earth and we have the gravitational force acting. Here's your equation works. But I kind of said, I'm going to be easy or lazy and just go along the axis. Does that work? I mean, what if I said I tossed it out like this and it takes some parabolic path? Would it still be the case that I could find my change in potential energy at that point? Yes. Because what we just covered, which is conservative forces, the path independence. I mean, this is a consequence that you're seeing. In a lot of cases, if you didn't have this kind of situation, it would very much matter if I deviated from this path at all. It'd be absurd to say that they're the same. But here, I don't care about anything other than I started at some position, I ended at some other height above that I'm measuring along the y, right? And that tells me the change in potential energy. And so I don't care about any of those path deviations. That's my answer. That's one of the consequences that makes it so powerful. So let's do the spring mass system real quick. Now, with the spring mass system, same thing. I'm going to go back to x here. It's convenient to use xi, x final, the force. So can anyone tell me from Hooke's law whether it was our force here? That's what we've been dealing with today with the spring mass system.
Hand choke. This guy's still teaching.
Okay, very close. There's one important factor. If you're saying you're displacing from equilibrium, does that spring want to keep pushing you away, or does it want to draw back to equilibrium? Exactly. So what we do is we give that a negative sign. This didn't come out well. This is a negative here. So we need a negative K. And that just means it's a restoring force. So as opposed to like light charged particles that want to repel each other, the spring always wants to draw back to equilibrium. Okay? And so we have a negative xi to x final, and a negative kx dx. Now here it's not a constant. So we do our integral, the negatives cancel, we get a 1/2 kx squared from some initial to some final, right? And so change in potential is equal to 1/2 k x final squared minus x initial squared. You may not have seen it in this form, but in a second, just like what we did over here, we'll get down to one simpler. We can call, when the spring isn't stretched at all, that's equilibrium, right? It feels no force. We'll call that our zero. It's very convenient. And we'll say that happens when x high, the initial, and that's at 0, right? So measuring from the relaxed length of the spring, then we can say that this is u, this is a function of x, is 1 half kx squared, and this you probably see. These two formulas, I mean, as well as the ones that precede them, are very important. You certainly want to have this written down and know it for tests in the future for homework. But so here's for a spring mass system, measuring potential energy as a function of position, and this is for the gravitational potential energy. So while you guys finish writing that down, we'll try to get into conservation of energy, which is again a very important topic and allows a lot of simplification from the standard Newtonian dynamics that you've been doing so far. Okay. Can anyone tell me if I'm just focusing on mechanical energy, right, and it's mechanical, by definition, what is this equal to? So we've been talking about potential energies today, we've been talking about kinetic energy, and now we're going to kind of link the two together. Anyone? That's right. So the sum of both, which I'll say K plus U, by definition, that's our total energy in the system. All right? Now, there's a couple assumptions that we're going to make. So I'll say one is that only conservative forces. Conservative. And again, most of the time we'll just be dealing with conservative forces. So what I'm about to explain, just conservative forces. And then two, isolation. So it's isolated from the environment. Okay? Now isolated just means if I'm looking at some object and I'm saying, what's its energy? I want to assess its total energy. I can't have the environment interacting with it, pumping energy into the system, taking energy out, right? If I have a system, let's say the Earth and a ball and tossing, then certainly the gravitational force is okay. That's not violating this isolated part. I couldn't come along and smack the ball with the bat and say, oh, you violated conservation of energy, right? As long as I'm within that system and I'm only dealing with conservative forces, what the things that I'll discuss in a second will apply. Okay? So if work is equal to the change in kinetic energy and negative work is equal to the change in potential energy, this is kind of like what we were talking about at the beginning. And we're just setting the two equal here, or if I take the change here, I say that the change in mechanical energy is equal to the change in kinetic energy plus the change in potential energy. Right? Now, if I do this, then I can just say that this is equal to Kf minus Phi, right? And this is equal to UF minus UR. Okay? Now, sorry. All right. And I can conveniently, I'm just setting them equal but negative through their work. All right. And now I want to rearrange this, and this will be something you definitely want to have written down. Ki plus ui is equal to kf plus uf. Okay. So all I'm doing is I set them equal to changes through their work. So I took the negative over here. That's the negative sign. Now I'm rearranging that thing. The initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. All right? And so what that means is if I'm looking at a system under these assumptions where mechanical energy has to be conserved, then if I know if the sum of its potential and kinetic energy at one instant in time, it can't change from that. It has to remain that value for all time in that system. And so many of these problems you'll see later when we do work out the homework problems, that's going to give you a huge reduction in the work that you have to do or how difficult the problems are, as opposed to with all the forces, you instantly know this is something you can go back to, or if you're looking at collisions between particles, things like that. But using this will allow you to greatly simplify the problem. So, one last thing. If these two are negative, one is work, one is negative work, this is 0. probably should start. And again, I'm being specific saying mechanical energy because if we have time, we'll talk about a different form of energy in a second. But this is the statement of conservation of energy. And that's how we get here. We're just saying that the total mechanical energy in a system, if it's conservative forces that are acting in this isolated fluids environment, has to be conserved. And so that's this, I mean, there's never been a violation of conservation of energy by any experiments. This is one of those things that's really held up through all experiments. And it leads us to using this, which can help us in a lot of the problem. I think we're going to forego the demonstrations today to get the last couple of things out. But the idea here is conservation of energy. If I roll this ball down, supposedly it'll come to the same height here, passing through full kinetic energy here, so we'll see if it's set up correctly, but pretty much. So again, completely, all the potential energy, there was no kinetic energy when I held it here, right? If I place it here, it's all potential. It completely assumes kinetic energy here because I'm defining this as my 0 point for potential energy. By this equation, energy conserved. Now, it didn't quite reach it, and there's tons of problems here. I mean, we have friction in the trap, all kinds of things that violate what I've said here. But approximately, that's a pretty good system. That's showing you this really, I mean, it really works, that all that potential energy is turned kinetic. It has to go up to the same height. If it didn't, it would violate this principle. Okay, so I think that's probably enough about that. One of the really important things, and maybe it'll be the last thing that we talk about, is this, the potential energy curve. Okay? So if you guys, you may, this is, I think I'm using the exact diagram from the book, so if you don't want to write it down right now, just jot down the points, that's fine. Are you guys familiar with potential energy curves at all? So I mean, it kind of looks like a lot of squiggles, but it's one of those things that's incredibly important. It has just an amazing amount of information stored in one diagram. So the first thing, before we get into that, another equation that I should mention to you, so I'll erase this. And of course, all these equations, if you don't get one written down today, they're at the end of chapter 8. But because if you start from changing u as negative work, and you use the definition that work, even for a varying force, if I take a small segment like house and last class at the end, I take some small change in x, I can approximate it as a constant force, and this is change in u. If I just solve for f of x, right, I get that it's the change in u over the change in x. Now in the limit, that change in x at intervals is very, very small, which is the best I can do, because the smaller that it is, the more constant this is. Sorry. And the limit, if that goes to 0, this becomes a derivative. And so you have a relationship that, again, you'll use countless number of times here, and the derivation is applied. So starting from this, which we started with at the beginning of class, you can get that the force related to the potential energy, the change in potential energy, is through this negative spatial derivative. Okay. So with that in mind, this plot should hopefully make a little more sense. So up here I have the potential energy as a function of position, and I just drawn some arbitrary path. This doesn't really mean anything. Below it is its force that's associated with this potential energy. Okay. So I'll give you a second to think about it. It's associated through this negative derivative. Okay. So if you were to go along and you think about the slopes of tangents, you should see that this is like a maximum, there's a 0, right? I started as a really negative slope here, so, but I'm using the negative, so this better be the highest positive point. That's the largest negative slope, okay? As I go down, I reach another minimum distance. The slope is 0. I have a 0 here at the poles. Same pretend this is a bad drawing, but that's a maximum there. The slope there is 0, so we have a 0 at x3. Okay? So if someone gives you a potential energy curve, immediately you know the force that's exerted on that particle by reading off this curve. You compute that, so they're inherently linked together through that derivative. All right? Now, a couple important points. if I say that u of x plus k of x from our definition is equal to some constant of mechanical energy, and I rearrange this, I can write it as E mechanical minus the change in potential. Now I'm doing this on purpose because I was given the potential energy curve. This is the thing I have knowledge of. Force doesn't really matter here. I'm just saying you can also get force from it. So why is this important? Well, there's something that we know about kinetic energy, and that's that it's 1/2 mv squared. It can't be negative, right? So if it can't be negative, it'd be unphysical if it were negative. So if I tell you the total mechanical energy, which is conserved with these assumptions, that can't change. So what would that look like if I were to plot the mechanical energy, just the structure of it? We got a lot of wiggles over here. What would mechanical energy look like? Straight line. And straight and horizontal. Because it can't, if it had a slope, it'd be changing its position with respect to position. So I'm going to say, let's pretend it goes, and pretend that's straight. If this is E mechanical, the line here, there's something very significant about this point in relation to what Can anyone tell me, if I were a particle and I'm coming along, that it's an initial kinetic energy to the left, I reach this point, what's significant about x1? Does anyone have I mean, very much looking at this, thinking that this is reading off the potential energy at that point. The kinetic energy is 0. So that particle had to stop. And that's right. Now, could that particle go into this region here? So looking at this and knowing that it's 0 here, it can either just stay there, or that's not going to happen. Could it go to the left? The reason it can't go to the left, and it absolutely can't, is that if it's 0 here, and we're subtracting u, and u is clearly greater than the total energy here, it would mean we have a k less than 0. That's not possible, okay? You can't have negative kinetic energy. So what you can do is put blue dashed lines here and say that's a forbidden region. The particle could never go over. All right? So now you can also, this is how much information these kinds of plots have. Not only can you say, here's a region of space that particle can't go, but looking at our force, what kind of force, or I should say, is there a force at x point? So you could, if you didn't have the bottom plot, you could take the derivative. You can see there's a huge slope here, and it's negative, so there's a huge positive force. Does that make sense? Now, positive is defined as to the right. So what it's telling me down here is not only it stops for a second, but I have a huge positive force in the right direction. So it's not going to go to the left. That's impossible. It's not going to stay there either. It's going to feel this large force to the right. It's going to make it turn around and go back down. Okay? This is called a turning point. Again, this is all in flow, but those are significant for a lot of reasons, but it's a turning point. It can't go to the left. It'll be forced to go to the right. Now, if the particle were sent back down and rides along this curve, let's say it gets into this region.